Hello, everyone. Okay, let's keep talking. We're going to stay with chapter 27. If you're following these more or less in order, we did chapter 27 last time, but the problems we had done last time from chapters 27 of the 17, like I said, there's 17 problems here. They're all going to scroll at the end of the video, any video that's associated with chapter 27, these 17 problems. Let's make sure we got that. 3, 6, 10. What am I talking about? A total of 17 problems, not even counting the extra ones, is actually what's going on, guys. We have a situation of 3, 6, 10, 14, 17, 19, 20, 24. Of the 24, we have, let me just see here. Are there 18 of these? For some reason, yeah, I could have sworn there was not quite as many as that, but maybe there is. Okay, so the bottom line is, guys, we've got a total of, make sure that was right, guys. I actually had that there. Just wanted to agree with the previous stuff that we had done, guys. It's what we're going to do is what we're going to do, and what's going to scroll there. You're talking about a situation, 10, 14. Okay, I got a total of 17. So, hope I didn't circle something that I was not supposed to circle. See what we got here. 3, 6, 8, 10, 13. Right, 17. Of the 17, we've already done these, you guys. We've done 7 in the previous video. We've done 7, 8, 9, 13, 16, 23, 32, 33, 40, 45, 49, and we're going to try, to our best of our ability, we're going to do the remaining problems, which are 52, 61, 62, 83, 86, 88. So let's go with that. Let's go with 52. 52, I'm largely going to talk you through it, and you're going to see it scrolling at the end of the video. For problem number 52, they are asking some pretty fascinating questions here. So let's look at it. It's a part A, part B, and you got to explain in terms of the amount of work needed in each case, how these actually work out. Problem number 52, imagine charging 2 capacitors with a hand generator. The 2 capacitors are identical except that one has air between its plates and the other has a dielectric. A, if you wish to store the same amount of charge on each capacitor, which one would be more difficult to charge? B, if you wish to have the same potential difference between the plates of each capacitor, which one would be more difficult to charge? Explain your answers in terms of the amount of work needed in each case. Quoting from the answer key associated with Dr. Katz's book, for A, given that, and like I said, a lot of this is going to scroll for you. A lot of the writing that I have here, copied from Dr. Katz's beautiful work, you'll see it at the end scrolling. Dr. Katz has done a great job in so many ways in this book. Given that Q equals CV, if there is a fixed charge, the capacitor with a dielectric, which has a larger capacitance than the one without, will have a smaller voltage across it. The work needed to add charge to the capacitor is this. So the work needed to add charge to a capacitor, not really Q delta V, but at least for a piece of charge, right? It's 1/2 QV. Either that's a misprint somewhere on somebody else's part or on my part. If it's a set amount of charge and then one shot there, you can put it as 1/2, or you call it Q delta V. if you're doing one, you know, this is true, and then the other way that you see it written, I believe it's arguably true also for one piece of charge when the delta V is at a constant. So both are true. It depends upon what you want to say regarding it. This is if it's a fixed voltage and a fixed potential difference and the amount of charge Q, you're fighting to move it over somewhere. You're trying to get charge Q working against this amount of potential difference working against you, working against that amount of potential difference for one shot. So the capacitor with the dielectric, same Q and smaller V, requires less work. So again, there's a lot of ways you can do it. I didn't quite do it this way in the notes, but we know that Q is equal to CV. Right. Well, we know Q equals CV because C equals Q over V. Depends how you want to write that as well. We can argue that all day. But, you know, the V or the delta V. Let's just put it this way. A capacitor, you know, the same Q and smaller V requires less work. So in other words, if the dielectric, if this is the capacitance associated with air, and you multiply it by V, that's the amount of charge you got on there. If you can get it to the same charge V, but the dielectric associated with the capacitor you originally have brings you to a higher capacitance, the amount of charge there is KQ. Well, they didn't really ask that. I guess another way you can kind of put that is, if it's something looking like this, if you want to have Q, and this is kappa times C for the dielectric, to get that same Q, you don't need a potential difference across the plates of V. You need one that's V over kappa. V over kappa times C. V over kappa times C. The kappas cancel, you got CV. You got the same Q here. It's the same Q as this one according to the mathematics that goes on. Well, if that's going to be the case, this right here is a smaller potential difference than that is. So, I mean, for the same Q and a smaller V, I guess you could say it requires less work. So if you're going to say something like this, again, it's not really the best way to have put the whole matter. There's you know, sure a whole lot that goes on. Best way to kind of look at it, I mean, this is true for one piece, but for the whole piece, the whole situation that's going on, say a lot of stuff. I mean, you could say, you know, there's a lot of formulas, guys. I mean, you know, there's when you talk about this stuff, you know, it's 1/2 C V squared C is Q over V. So I'm going to get to that in a second. V is Q over, you know, V is Q over C. If you solve for V right here, multiply by V on each side, divide by C. V is Q over C. The quantity Q over C squared is Q squared over C squared. So we got that. So I wasn't sure what they were doing with their notes when they had the Q delta V. It's certainly proportional to that. You got to put the half in there to kind of make this whole thing work out. 1/2 Q delta V or 1/2 QV for what's going on that way. So you had all this. Well, how much work is required? It's easier, literally it's easier to get the same amount of charge on a capacitor with a dielectric constant of kappa bigger than 1. It's easier to get the same amount of charge on there. What does that mean? Less work to get it done. Why is it less work? Because by the time you're done, you've only charged the plates to a voltage, to a potential difference. You've only charged the plates to a potential difference, which is V over kappa, which is kappa times less than what it would have been without the dielectric. So there's a smaller V there. So basically you're looking at a situation, if I was looking at one of them, I'm looking at W as 1/2 Q delta V or QV. That's without the dielectric. A lot of voltage I got to put, a lot of potential difference I have to overcome. The other one doesn't create. You're going to do the same thing with the other one. To get the same amount of charge on there. So this is charge. Let's put a charge. I don't know how to say it. I mean, I guess I'll just call it W1 is the first situation where there was no dielectric, and here it is with the dielectric. So, a lot of ways to write it, I guess you could say. You could say for no dielectric. I'm going to try to make the language make some sense here. No kappa, and this one's associated. There's no kappa, so there's no dielectric constant that you got to worry about. The dielectric constant here would be 1, so maybe 1's a better way to write it. And the other one's kappa, which is something bigger than 1. What work is required with the same amount of charge Q? Well, with the same amount of charge Q, well, we said if you wanted to get the same amount of charge Q, you need a potential difference, which is less. At the end of that, it's going to read a potential difference that's less. So it's Q V over kappa. The work required without a kappa that's equal to 1, just with a kappa equal to 1, with no kappa bigger than 1, the work required is 1/2 QV. With a kappa, it's 1/2 Q V over K. Or V over kappa, rather, I'm sorry. Everybody cancels. They go, the V's go, the kappa comes on top. Kappa times more work is required. Kappa times more work is required to do it. With the same Q and smaller V requires less work. Yeah, you're going to need more work. That much more work, that many times more work. Put another way, in association with the kappa, you're going to need the work associated with the dielectric is going to need 1 over K, 1 over kappa times the work to do it, to actually get the job done, all other things equal. Because you're using this. Okay, so that's some of the talk on that one. So basically what you're talking about is You know, so the capacitor with the dielectric, same Q and smaller V, requires less work. It's as simple as that. That was A. B, what are they asking there? They're asking if you wished to have the same potential difference between the plates of each capacitor, which one would be more difficult to charge then? You said the same charge, huh? So let's see here. You wanted to charge it. Let's see exactly how I said that there, how they say it too. If you wish to store the same amount of charge on each capacitor, which one would be more difficult to charge? Same amount of charge on the capacitor. Okay, if you wish to have the same potential difference between the plates of each capacitor, which would be more difficult to charge there? The capacitor with the larger capacitance will hold more charge for the same given voltage. True. If delta V equals delta V for both circumstances, so the same amount of work was required with the same potential difference. If the same amount of work is transferred, if the same amount of charge is transferred is the same. But since more charge, more work. So let's, this is easier, a little bit easier done than said, I think, as so often can be the case. All right, so you saw the basic argument for 52A. Let's look at 52B. So the question itself, I mean, there's a little bit of confusion with some of the questions, I guess, but we can kind of give it our own look to it, and I think make a little more sense. So if you so what was 52A again, guys? If you wish to store the same amount of charge on each capacitor, which one would be more difficult to charge? It's easier to charge a capacitor that has a dielectric between it than one that does not. Okay, that was for A. So we kind of talked about that. So let's kind of forgive me for kind of digressing with that a little bit, guys, but same Q and smaller V requires less work. It's as simple as that. So it's going to be a smaller V to get there, to have, same Q, that you're getting the same Q, but you got a smaller V. They're kind of going along the same lines here. Now, in a sense, if you wish to have the same potential difference between the plates of each capacitor, which one would be more difficult to charge? Explain your answer. You wanted the same potential difference. So, there's a lot there. There's a lot on that one. Well, you remember, we said a number of things. I mean, with the work required and the U of E, and then the work, they go hand in hand. You're going to give it that kind of potential energy, so it's going to be in that regard. When you look at something like this, let me just try to. Yeah, we already talked about that. That's just going to come out to 1/2 QV. Same thing can be written as 1/2 QV or Q delta V. You kind of use them interchangeably. Just be careful of the language we're using on this kind of thing, guys. Q is C times V. Remember, we said that C, of course, was Q over V or Q over delta V. So Q equals CV. The one that's probably jumping out at me more than anything else is that last one. And that's how they kind of talked about it as well, because you already know the capacitances. They're all valid. They're all equal. They're all going to work. Just be careful. Well, I think, like I said, I think this is a good way to go. There's a lot of, I think perhaps there's easier ways to go, actually. If you were to have, so many ways to go. I mean, these last two kind of jump out at me as being giving us a good look at what we want to do, guys. You wanted to have the same potential difference. I don't know what happens when you have the same potential difference, necessarily. What happens to the charge? You're not having the same charge. You have that where the capacitor with the dielectric has K times less potential difference between the plates at the end of the whole story. At the end of the whole story, you need kappa. At the end of the whole story, you need kappa times less potential difference between the plates of a capacitor associated with a dielectric when compared to a capacitor not associated with a dielectric. You need kappa times less potential difference to accomplish the same charge. You need kappa times less potential difference for the capacitor associated with the dielectric as you do with the capacitor associated with no dielectric to have the same charge. Kappa times less potential difference for the dielectric to have the same charge as the one not associated with a dielectric. Kappa times less means V over kappa. And you saw me do that argument. But if the V is the same, it's a different dynamic. Q equals C times V. True. With the dielectric of dielectric constant kappa, kappa times this C. Kappa times this C is the capacitance associated with the capacitor with the dielectric. Kappa times C is the capacitance when you have a dielectric associated with a kappa. Yeah? Well, that's your C then. What's C times V? Well, wait a minute. Didn't we already say that, this right here, kappa times this, pull that out of here, you got CV. Yeah, I know, but CV was Q. That's Q. So at the end of the day, everyone, yeah, if you got the same voltage, if you have the same potential difference, if you can get it to that same potential difference, yeah, you got more charge that got moved over there. So yeah, more charge got moved over there, so how much work has to get done? Use this one. This is W sub E sub 1 for the kappa equal to 1, no dielectric, we'll say. And that's 1/2 Q V. The other one's going to have the same V. Correct. But it's going to have kappa times Q charge associated with it. And that's going to be WE with the kappa. WE associated with the kappa is, pull the kappa out of there. This is just a 1 right here, or don't even put a 1, doesn't matter. But the work to charge up to the same potential difference compared to the work. The work to charge up to the same potential difference as was initially present without a dielectric. The work to charge up with a dielectric present. The work required to charge up with a dielectric present compared to the work to charge up when there's no dielectric present is, you're looking at it, guys. I mean, figures into it. Ratio of kappa. More work. You don't get something for nothing. Yeah, okay, the capacitor helps you out. If you want the same potential difference between the plates, you're going to do work to do that, but you're moving more charge. So you're reaching, you're having to move more charge and more, even at the differential level, you're moving kappa time even at the differential level. One's dq at the differential level, dq movement of charge, and the other one's kappa dq movement of charge. For the same potential difference that is being encountered every time. Every time you are going through a particular potential difference, the one associated with the dielectric, you're going to move more charge. However, moving more charge is still, kappa times more charge, kappa times more work. You don't get something for nothing. It shows up. It shows up. So, if, it's kind of an interesting point here. I mean, if you had, the way it gets, you can argue it a bunch of ways actually, but, for more, it depends, the mathematics kind of rules the day. I say a few things here, don't need to necessarily repeat them, but the same, for both circumstances, if the potential difference is the same, the amount of work would be the same if the Q delta V was the same in all instances as you're making the movement. It's not happening that way. You're getting you're getting K times dQ more charge with every amount of potential with the amount of potential difference that you're fighting to get the charge to get over there. You are getting K dQ to get there, kappa dQ to go there. So it's going to be more. So there's a lot that gets said. I said a little more explicitly. I said it a little different way in the writing of the notes, but it's neither here nor there, guys. It's going to work either way. We know that. Is there another way you could have looked at it somewhat more generically, but still kind of answering the same thing? Yeah, I mean, we're already sort of more or less making the claim, you guys. We know, I mean, as a general rule, you saw me go about it along this path. You could have gone this way too. What do you mean? Well, we already know as a general rule what that means. So then we say, there's a whole lot to say. I mean, the voltage across the capacitor, 1/2 C V sub C squared. We're making this claim. E, the dielectric. I wrote it as dielectric. I'm going to write it as kappa again. The air, UE1, we're going to say it's just more. I'm I'm going to stay with that notation, but when you read my notes, you'll see I have the subscript dielectric, and I have air. When you go with this, you got essentially 1/2, agreed, the dielectric, C associated with the dielectric, so we call it, I'll say associated with a kappa right here, and this is Vc squared, and I think we're simply compelled, guys. I kind of ran out of room here. I don't know if it's the best spatial choice here, guys. That's bigger than 1 over C with a kappa of 1. Look, I mean, you can cancel the half, you can cancel the halves, you can cancel the V sub C squareds, equal potential. C sub kappa is bigger than C sub 1. It's the same argument. You're coming down here, and it should work out just fine. Okay, guys, that was 52. 61, find an expression for the electric field between the two conducting disks. Make sure your expression is general enough to include the possibility of a dielectric between the disks. Check your answer using the information given in section 27-8. Okay, let's see what we got. Okay, I mean, that's an interesting conclusion, interesting question that's being asked there, guys. Let's, let's read it again a little bit and then kind of go with it. Find an expression for the electric field between the two conducting disks. Make sure your expression is general enough to include the possibility of a dielectric between the disks. Check your answer using the information given in section 27-8. Let me make the disks and let's see what's going on here. I mean, there's a lot of, this is kind of, it's a little on the wide open side, guys, in some sense, because as far as the notation you're going to use, there's a lot that you're not being told. Okay, so I'm trying to get some decent illusion of what's going on here. That's R. That's also R. Kind of just, this is just for the drawing itself, not necessarily that it's contained by anything, but just to kind of give the illustration of some space there, guys. And something like that. So see how we did the argument. I mean, there's a myriad of ways to go here, guys. I'll try to make it very obvious as to what you're going to say. See if they actually said anything about it. All right, they sort of gave an answer here. I just want to, the hard thing is to kind of figure out what's going on. Okay, let's kind of read a little bit of this. One's with the dielectric and one is free. How are you actually going to say this? On page 855, the people with the book are going to be able to know this, see this. Let me just go into it a little bit. Gauss's law on page 855 and beyond it a little bit. Gauss's law in a dielectric. When we studied Gauss's law in chapter 25, we assumed the electric field existed in a vacuum. In that case, the electric flux, we assume that the electric, now see, they want us to be able to put a kappa in there. And so yeah, they were serious. I mean, so we got to work with that. When we studied Gauss's law in chapter 25, we assumed the electric field existed in a vacuum. In that case, the electric flux through the Gaussian surface is proportional to what they had said here. And I got that in the notes as well. Let me just kind of try to let me kind of define some of the language being used. The way we were initially talking about it, when the electric field existed in a vacuum and not in a dielectric, we said something along these lines, which we've already seen a number of times. True. Now a lot happens. So let's talk about it a little bit. We can modify Gauss's law to include the presence of an insulator, such as a dielectric, between the plates of a capacitor. Okay. To answer that question, let's consider a parallel plate capacitor. First, remember that we have used Gauss's law to find the electric field between the plates of a vacuum-filled capacitor. And we were saying that, okay, if it's in free space, they call it Q free. So let me just kind of, let's kind of like define some of the units, some of the language they're saying here. We've talked about E within a vacuum, and that's essentially meaning, you know, what would it be, what's the Q associated with the vacuum? So we'll call it Q free. On the plates that go on there, free of a dielectric. And we got this. And there was, in the non-calculus based discussion of this, we were actually able to prove this using calculus in a sense. So if you look at some of the lectures that I've done elsewhere, ostensibly non-calc treatment, for the heck of it, we use some calculus, and we escaped having to use Gauss's law to be able to derive something like this. So you might find that of interest. There was calculus used. The students, obviously, in the non-calc version of the class did not have to know that, but it's, but you can know it if you want. They're not really asking you for a derivation. Well, here they kind of are, but I'm not going to be asking you for a derivation on the exams necessarily. Okay. So what do we have here? So the reason for adding the subscript free is explained below. Next, imagine a dielectric consisting of dipole molecules between the plates of an uncharged capacitor. Because there is no electric field, the dipole molecules are randomly oriented. Any Gaussian surface you could imagine would contain no net charge because every molecule is neutral. Even if the Gaussian surface happened to pass right through the middle of a few molecules, it would include positive charge from some other molecules and negative charge from other molecules, with no net charge overall. Now imagine charging the plates of the capacitor so that there is an electric field inside the dielectric. The electric field causes the dipole molecules to line up such that the negative side of each molecule is closer to the capacitor's positive side, and the positive side of each molecule, so the electric field causes the dipole molecules to line up such that the negative side of each molecule is closer to the capacitor's positive plate. Now our Gaussian surface encloses the excess positive charge, Q free, on the capacitor plate. Also, our Gaussian surface no doubt passes through the middle of some molecules, preferentially enclosing an excess negative charge because the negative sides of the molecules all face the same way. So there's going to be a situation when they're actually doing this. Let's see here. Preferentially enclosing an excess negative charge because the negative sides of the molecules all face the same way. So the total charge Qn inside the Gaussian cylinder is the charge Q free on the surface of the capacitor plate plus the excess negative charge from the dielectric. So what happens in a sense is there's going to be an excess of negative charge. We're going to do it in such a way that we're going to enclose a little bit more of the negative charge, you guys. So so the total charge, so let's see here. So the total charge Qn inside the Gaussian cylinder is the charge plus Q free on the surface of the capacitor plate plus the negative charge Qd from the dielectric. We substitute into Gauss's law and solve for the electric field inside the dielectric. So the actual premise is, when this is going on, I guess it's a fascinating point in its own right. You're terminating the Gaussian cylinder at some point, so there's going to be an excess of negative charge. The way it's set up here, so it doesn't seem incredibly. It's a little different dynamic. Since you're going with the positive charge, the negative charges will somehow be more prevalent within the dielectric, at least in the Gaussian surface that you enclosed. That's their argument. Qn is going to be Q free minus Q sub d, and that's where they're getting some of the look of what we're doing here, guys. So what we could say is basically we're looking at it in such a way that somehow, because of we're dealing with the positive plate, there's going to be an excess of negative charge closer to the positive plate than there is going to be positive charge close to the positive plate. Positive charge is going to be away from it, close to the negative plate predominantly, but in the Gaussian surface that we draw, we're going to say there's an excess of negative charge. Why is that? Well, at the end of the day, in an equivalent fashion, you're talking about the net E field. I guess maybe a better way to put it, and I wish they would have kind of said it in this manner. the E field itself is going to be smaller. So you can, in that sense, say there's an aggregate of negative charge. There's a preponderance of negative charge in one view or another, such that positive and negative, there's a bit of a cancellation going on. The E field associated with the dielectric is not going to be as strong as the E field associated with the vacuum. Why is that? Because there's not as much net positive charge present once you put a dielectric in there. That's the argument. It's still not a great argument, but that's essentially a good way to look at it. So when you say this, you could say that the Q in, if you're talking about the dielectric, it's still going to be the Q of the free, and Q sub D is minus a positive charge, or plus a negative charge, however we want to say it. But there's maybe minus a positive charge sounds pretty good to me as well, or the same as plus a negative. In a sense, you don't have effectively as much positive charge associated with the Gaussian surface in totality. The E field is not going to be as strong. Well, if you look at that, we substitute this and solve for the electric field inside the dielectric. And I'm just trying to use their language, guys, so forgive me. I'm trying to keep looking at the situation here. I want to make sure we're all, because later on I might write it in a different way, but let's at least start agreeing on some things. E sub total is the Q in, which is Q free minus QD, so that's the Q in divided by epsilon naught A, and how that can be done. You can do it, and you can prove this thing through using Gaussian surfaces. There's other ways to look at it in a sense. I'm tempted to do it now. I may have the notes, I may not. I don't think that I do actually pertain to what I did earlier on that, but that's okay. I mean, well, let's possibly come back to something like this. We substitute into Gauss's law and solve for the electric field inside the dielectric, and you're getting this. And this is kind of interesting. In a sense, by hook or crook, there's less net positive charge present because of how this thing's been aligned. The dielectric is going to set up its own E field. It's going to set up an E field that opposes the E field that was initially present before we used the dielectric. There was one direction for the E field before we had a dielectric in there. Put a dielectric in there, and the molecules inside the dielectric assign in such a way, or align in such a way, that there's a contrary E field, a counter E field going in the other direction. It's going to be a smaller E field. Well, how could we account for that? Well, we could say that somehow there's a net, in essence, there's a net positive charge that's less than what we had earlier. Less than what we had earlier is the net positive charge now, to give you the E total when you put the dielectric in there. This is the total electric field that results from the charged capacitor and the dielectric itself. Let me say that again. This is the total electric field that results from the charged capacitor and the dielectric itself. The dielectric's electric field is in the opposite direction as the electric field produced by the vacuum-filled capacitor. So the total electric field is weaker by a factor of K. E total equals E vac over kappa. Is total by a factor, is less by a total of kappa. To find an expression for the charge Q in inside the Gaussian surface, substitute and do a couple things there. So basically what we're trying to say here is, if this is the case, and you've got a capacitor, you're essentially building a capacitance that is going to be kappa times bigger than it was earlier. You know, what can you say about that? Well, if the capacitance is like that, you can say, I'm trying to argue here how I'd actually want to say something like that. Well, I mean, maybe this is where the definition itself comes into play, and then from there we can kind of work backwards and talk about some of the stuff we were already talking about. You're looking at, see exactly, let me kind of see if we can all agree on this. This is going to be smaller. I mean, we know that E total, the E field, is going to be less than it was here. Sure, because you have got a counter E field that's fighting. This was the E field without there being a counter E field fighting it. When there is a counter E field, you have this minus the E field that's being produced by the capacitor. So that's a big thing. So what you look at is, this is the total electric field that results from the charged capacitor and the dielectric itself. The dielectric's electric field is in the opposite direction of the electric field produced by the vacuum-filled capacitor, E vector sub vacuum. Yeah, it's in the opposite direction. So the total electric field is weaker by a factor of kappa. They just kind of didn't really give us an explanation for it, but they're just telling us, look, if there is by definition, let's set the definition associated with this. Well, you got the E vacuum, divide it by kappa, and you get the E total. And you get the E total. So if that's the case, what do you have to say? Well, we got a lot to say. We can say that E total is Q free. Let me just use the same exact argument that they're using. If that's the case, the total is going to be what the vacuum was, put a kappa right here. So E vac equals Q free. Forgive me. E total equals E vac divided by kappa. So divide that by kappa, you got the E total. So the E total is the E vac for vacuum true. That's what E total is. And that's equal to yeah, my order's a little off, guys, but it should be all right. That's Q free, what it would have been in free space, or you know, as you're trying to overcome that, and you got this. Absolutely. So from here, let's tinker with this a little bit. Let's see what Q in is. Now we said this was Q in right here. So, you know, remember we kind of as a by hook or crook, we said there was going to be the equivalent of less positive charge on the plate or less positive charge in the Gaussian surface. Within that Gaussian surface, there's less positive charge. So within that Gaussian surface, there's less positive charge. What is the aggregate amount of positive charge that's in there? Well, here's what it would have been, and it's this much less, and it's equal to this. And that's equal to, Q in. This guy is Q in. Q in, Q in. So what do we got here, guys? Well, what it means is take, you know, by hook or crook, guys. I mean, as I said, not to really make the point here. And there, look at that. I mean, look at that carefully, and get the Q. And this is the Q in. I mean, this right here is Q in, and that's also, I mean, that's Q in. In essence, the Q in, when there's the insulator present, the dielectric present, it's what it would have been, the amount of charge, take away a certain amount of positive charge, and that's really the aggregate amount of positive charge contained within that Gaussian surface that we can work with. It's a smaller amount. Why is it a smaller amount? Because the E field is smaller. The E field is smaller. So what do we have here? Q in multiplied by epsilon naught times A on each side, and Q in wow, starting to get some of the numbers we were talking about last time. And that kappa's doing a lot of stuff, isn't it? Yeah, there's kappa times less. Doesn't that sound familiar? We did something similar to this, how we solve things using kappa, and the kappa is what it is. I mean, the kappa, it's going to be kappa times more or kappa times less or whatever, but it's going to be some factor of kappa. Take this divided by kappa, and you got Q in. Okay, that might be. So that's in a vacuum. Now look, let's get something straight. I mean, if kappa is equal to 1, it's in a vacuum. If kappa is equal to 1, it's in a vacuum. Q free equals Q in. If it's in a vacuum, you just got Q free. When it's not in a vacuum, you got, it's Q free divided by kappa. The Q in is going to be Q free divided by kappa. Q free divided by kappa is Q in. So that's, and that would be in the presence of, generally speaking, E total, using their language. I just call it E. Later on, I think I'm just going to call the E total, just call it an E. But that's kind of where we're going. Based on what they've already said, guys. Based on stuff they've said. So that's pretty interesting. I mean, how that all works out. With the capacitor plates. Again, the big talk was things we've known from the past. We know Gauss's law pertaining to these matters. We have it right here. Let's work with it. Well, the in, there's a lot of ins. The general Q in, Q in over epsilon naught, the general Q in is Q in the way it would be in free space, no dielectric present, and then take away a certain amount of positive charge as the net total is smaller because the E field is smaller. So Q free minus QD, that's your Q in if there's a dielectric present. What does that mean? Well, it means Q free minus QD is the new Q in over epsilon naught times A. What does that mean? Well, if there's a dielectric present, by definition of what we mean by kappa, if you take what E vacuum would have been, divide it by kappa, you'll get what the E total is. Yeah, but what is that E total? Well, basically it's there. It's kappa times less. So it's Q free, epsilon naught times A, all of that, which would be in a vacuum, divide it by kappa, and you'll have it if you're talking about dielectric. This is what we said the Q in is over epsilon naught A. We don't need to use the kappa down here because we've already accounted for the opposing E field that's taking place. And together in aggregate, there's going to be an E field that's smaller than what it was before. It was small. This already accounts for the kappa. This thought process right here accounts for the kappa. So what does that mean? You got some Q in over epsilon naught A. What does that mean? Well, this right here is indeed the same it would be as the free, but K times smaller. This right here, that E field, would be K times smaller than what it would have been in a vacuum. And that's what you play with. You multiply by epsilon naught A on each side, and you end up getting Q free over kappa equals the Q in. And that's a good one to work with. If Q in is Q free over kappa, well, here's your Q in. It was Q in divided by epsilon naught A as a general rule, sure. Well, what would it have been in a vacuum? Oh, it'd be Q free, or divided by kappa. It's as though the aggregate amount the aggregate amount of charge is indeed, the big thing is, the Q in is kappa times smaller than Q free. Okay, so that's some of the argument that takes place with this. They explain it really, really well in the book. If that's the case, how are you going to write something like that? So you wrote it like this, and then you say, so much of this you don't want to erase when you're doing it, but we erase what we got to erase. Can we write this as a more general rule? I mean, and again, I'm using there, later on, for E, I just use, well, what they do is the E total. So let's see what we got here for an E field. This is pretty interesting. The E field's smaller than what it was. The E total is K times smaller E field. You know what? You'd get the same thing if you did this. Look over there. The integral kappa E vector dot dA vector E vector dot dA vector equals, well, what is that? It's, yeah, look how I did it. Be very careful here. There's a kappa here. If you multiply by A on each side, you got the EA over here, kappa epsilon naught. Leave the Q free. This would be the case if it was a vacuum. I'm not losing it. Is that true? Sure looks like it. I mean, this would be, at the end, we're talking about E times A times kappa equals Q free over epsilon naught, divide by kappa A divide by kappa A, you guys, Yeah, it's sure it works. You know, just what do you want to call it? Well, this is the E field associated if there's a dielectric. The total after all the tug of war goes on. Well, didn't we already say that over here? With all the games we were playing earlier, we were saying the same thing here. Absolutely. So here's where they're asking us for the general look. Can you give it this general look? Or can you put something general together and get that? Yeah, I'm claiming you can. We're claiming we can based on some of the stuff that went on. There's a lot to be said, you guys. I mean, just trying to think. Let me do something a little extra, if you don't mind. So we got this. We're trying to play the game that they're asking us to play, and we've got the machinery to do it. Q in equals Q free over kappa. Q total, Q associated with the dielectric, after there's the dueling E fields, it's essentially something we can view as, well, there's just less positive charge enclosed in the Gaussian surface. How much was there initially? That was what it was before you put a dielectric in there, and now you have less net positive charge with which to do an E field. Another way to look at it is, there's an E field within the dielectric, and there's an E field coming off the capacitor plates. They're fighting. The tug of war is won by the capacitor plates, but it does cost something. And that'd be the equivalent of losing some charge. It's another way to look at it. Qn equals Q free over kappa. So Qn over epsilon naught A, Qn over epsilon naught A is Q free over kappa. That's the Qn. And we proved that over here. We played all these games over here. We said it had to be, if it's this, it's got to be kappa less, because kappa by definition has that attribute of hampering the charge enclosed and thereby hampering the E field that is associated with what is taking place within the dielectric, within the capacitor. Because of the dielectric, there's less of an E field and in totality, and that's what's reflected right here. Okay. So we got this, you guys. We've seen it. We can kind of tinker with this. I just needed to get that kind of across to you, I guess you could say. Gauss's law is great. I mean, for sure, great. You know, you could look at this thing, and I did this, like I said, in a non-calc discussion of this very same thing. We talked about the capacitance being being an amount of charge Q over epsilon naught A, or I think there was some other way we had, let me try to think about that. I think it was, I have to look something up, guys, go back a little bit. Capacitance, I think it was something along the lines of you could find the E field with which you were dealing between the plates, and it's epsilon naught A over D, I think, and you could kind of try to actually see what I could say on that one. I think it was something along the lines of, let me not write it down until I get there. Right, so the capacitance, epsilon naught A over D, let me do something. Let me do a couple things here, guys. Again, there's a little bit on the fly I'm doing it here. It's been done earlier. We have this. We have it in the notes. have that. We can leave it, not leave it. Either way is fine. They're making this claim, epsilon naught A over D. What does that mean? And if it's in a vacuum, well, epsilon naught's a constant. The more area that you have, the easier it is for a given voltage to transfer charge. For a given potential difference, the more area that you have, the more charge can get moved. The closer something is, the easier it is to move something because there's more, you can induce charges to leave the closer you are. So for a given voltage, if you're close, that's good. So it's inversely related, capacitance is inversely related to the distance between the capacitor plates. The closer the capacitor plates are, the more charge you are going to move the way you want to move it and create a net positive and net negative charge. It's going to be easier for you to do it. The more charge you can move for a given potential difference, the closer you are. So it's inversely proportional to distance, directly proportional to area. The more area that's there, the more places, the more opportunity given a particular potential difference. If you can establish that potential difference, there's just more material there that can be moved for the given potential difference that you have, if you can keep that potential difference established. So you got this. I think what's really interesting here, guys, and like I said, we can kind of work backwards on this a little bit, is if you're looking at, let's look at with the vacuum right now, and then we can later on put other stuff. They don't have it in some of the stuff they're talking about right now. They don't. All right, they say that. Let's talk. Is it true that C is also Q over V? True. Is it true Q is Q and an E field, let's say it were a constant E field and you moved it through a distance D, and you moved a charge through a distance D, Q times E is the force, D would be force times distance, that's the work. Wait a minute, isn't potential V times, isn't Q times delta V the same as Q times E times D? So the E times D and the delta V are the potential difference. Well, that's interesting. I mean, we made a claim. It's EA roughly. I could say, how are you going to do this? We did it over here. We could say that for this up here, let's not use the kappas for now. Let's say you could get an EA somehow, and you got a Q somehow, and you got an epsilon naught over here. Why don't you divide by A on each side? We're going to talk more about this. You're going to say, okay, well, yeah, where did you get this? Well, we could do it with a Gaussian surface, and we got epsilon naught times A. Q over epsilon naught times A is what the E is. So that's, all right, let's believe that for now. We can talk a little bit more in the future regarding this. Kind of interesting what that's all about. I mean, because Q divided by A is a sigma, is area charge density. Q divided by A is sigma, epsilon, sigma over epsilon naught. Well, okay, neither here nor there. Let's just say this. I got a Q here. I've got a Q, and we got the E. Okay, we said the E was all this, Q epsilon naught A. Q over epsilon naught. Times D. The Q's cancel. The Q's cancel. The epsilon naught A goes on top. You got D. Wait a minute. This all looks very familiar. C equals epsilon naught A over D. Ladies and gentlemen, this is the exact same argument that you would do if I wanted to put kappa in there. I could play the exact, I mean, it's a little more wordy, it's a little more letters going on all over the place. But if you want to deal with it, yeah, it's going to be there. It's going to be there. What's going on with that kappa if you were going to do it? What's going on with that kappa? The kappa's on the bottom. The kappa's on the bottom of a fraction. The kappa would be right here. The kappa would be right here, and it flips upward. Kappa epsilon naught A over D. Oh yeah, it's a bigger capacitance if there is, because for less voltage, you have the same amount of charge stored. Okay, and we talked about how that's going to play. But there it is. You got this. And the E field sigma over epsilon naught between the capacitor plates. I don't know, that's not that obvious, to be honest with you, but you know, where's that coming from? This is some of the stuff we're talking about when we try to say this stuff, you guys. I don't have the notes on me that I used when I did this with the 120, but that's so what we could easily find. Let me just kind of just do this on the fly, guys. I don't want to keep you too long on this. I mean, I do that enough anyway, but is this making some kind of sense? Well, yeah, it makes sense. It all makes sense. It all makes sense, provided that this is true. When you're talking about the total, it's going to be kappa less. If you're talking about the total, it's going to be kappa times the size. Forgive me. If you're talking about E subtotal, it's going to be kappa times smaller size than this. It's going to be this divided by kappa. And that's where you can put the kappa right here. Because if it's that much smaller, if the E field is that much smaller, and you're still accomplishing this with an E field kappa times smaller, the capacitance must be kappa times bigger. If there's a kappa here, if there's a kappa right here, it flips up and comes to here. Okay? So something to kind of think about. Well, yeah, okay, again, we said that's okay, great. You want to talk like that? We want to say that? Here's the total, there's a kappa here. Do you want to, you know, it's as simple as that. We said where they are. The Q in is Q divided by kappa. So it's really Q over epsilon naught A. I'd like to find the E field to be, the E field coming from one plate, the positive plate, has got to be Q. The E field coming from one of the plates, the positive plate, has to be Q divided by epsilon naught A. Q divided by epsilon naught A will get me there. Yeah, all this stuff here. I'd like to see if that's actually true. You can do it with Gauss's law. It certainly works. Gauss, one of the greatest mathematicians ever. We can also kind of just look at it a little more, I don't know how to say it, to me almost a little more intuitively. If you want to look at something like this, you could say, well, wait a minute. Let's see what happens to one plate. See what happens to one plate. And then you tell, you know, let's just talk. I mean, there is, let's say you're looking at a positively charged plate. Let's say this positively charged plate, it can be circular, it can be rectangular, it can be triangular, it can be whatever you want, but let's pretend it's really big. It's really, really broad compared to the length between the distance. It's very, very broad, very wide, just a very large plate compared to the distance from plate to plate, from that plate to another plate. Could be something really big, whole bunch of positive charge on it. Sigma is the total charge on the plate divided by the total area. That's equal to, I mean, we can figure out how large this thing is. And we could say, we could start right here. Let's start in the middle. And some kind of middle. If this thing's really, really huge, it's hard to say what the middle and what the end is. That's capital R for the radius of this thing. And we say this thing can go on forever. And you can look at it, we're looking at it bird's eye view straight down. What's the area of any circle, I guess you could say? The area of the the area of the sphere, forgive me, the area of the circle for pi r squared. Yeah, we could also say this right here, sigma, is dq. Big Q, small q, doesn't matter. I mean, there's a lot of symbols, guys. That's just it. It's hard to, we got to be speaking the same language, I guess. We can speak any language we want on this stuff as long as we're consistent and the people who are hearing us are understanding what we're trying to say. dq dA. It is uniformly charged. Say it's uniformly charged, you guys, in some sense. Well, okay, all of that's believable. All three of those. If you were going to look and build rings, like there's a ring and there's a ring, and this thing right here, and you're gonna build these. You're gonna start from like here, which is like very, very tiny ring, to like a big ring, and you just keep going out. We're gonna say there's a differential length d small r, and if these are really, really close together, the size of the circles isn't big enough for me to worry about it too much. The size of the circles isn't really big enough of the two different circles here, so to speak. So you got this guy as a circle, and you got the other circle, and I'd like to just, it's right around there, you guys. It's around there. And if I go, this is 2 pi r times dr, this area, well, it's a differential area. Again, guys, I'm kind of going by memory here. I don't have the notes on me that I had used for the non-calc class when I actually did a calc version on this. But 2 pi r dr dA equals 2 pi r dr. Yeah, I think that makes sense. This is interesting. Is that true? I'll tell you what. Is A the same as pi r squared for any circle, no matter what size? I'm not talking about the big circle, capital R. I'm talking about, let's talk about this circle right here. Or let's talk about this circle right here all the way around. Let's call that a radius of R. You know, let's call this a radius of small r. And then this right here is this right here, this distance right here is, I don't know a good way to write this, guys. I just did it. The distance right there is dr. Wait a minute. How much do we know? A equals pi r squared. dA dr is 2 pi r. dA is 2 pi r dr. Yeah, it works. A equals pi r squared. dA dr is 2 pi r. dA is 2 pi r dr. So that's this area in green in its totality. Well, let's get all of those. Well, wait a minute. There's charges here. There's positive charges here. All the charges are equally distributed. They're uniformly distributed in there. If you got a positive test charge, ladies and gentlemen, coming right out at you, positive test charge coming right out at you, do you understand? And you're centered right here at the quote-unquote center of this infinitely large object, infinitely large area. If you've got a positive test charge right here, do you understand that all of these guys hit the positive, you know, every differential, every DQ hits this. This DQ hits it and goes that way. This other DQ over here hits it and goes that way. This one hits it and goes down somewhat. This one hits it and goes up somewhat. Yeah, I know. All these guys have a sideways thing going on that cancels out, and the net result is coming right out at us. If we are looking at how this thing looks, here it is. That's bird's eye view. This is a sideways view. We look at this thing right here at this point, and you've got, and you have you've got the disk coming out at a, you know what, I do not even want to try to draw this, honestly. You've got the disk, and it's, you know, here's a cross section of the disk, here's a cross section of the disk, and this guy's firing this way, this guy's firing that way, the other guy's firing that way into the board, the guy out here is firing that way into the board, looking just like these two. This guy, this differential DQ, and this same differential DQ size-wise goes like this. The other one goes like this. The guy over here goes into the board looking just like that. The one on the other side, opposite to it, comes out. There's going to be a cone formed, I guess, of E fields. All the horizontal elements of the E fields are going to cancel out. You got this guy, you got that guy, this guy's doing this guy's doing that. These cancel. The E field's that. I mean, whatever at the end. It's all going to be, the net situation is going to be a net E field straight up, nowhere else. So I'm not doing it with a Gaussian surface here. I'm doing it a little more, I don't know a good terminology for it, a little more, perhaps a little more intuitively, in a sense, you can look at it. But that's exactly what's going on. Well, let's figure this out, man. Because here you could do the same thing here. What's going on there? Well, there it's a little different story. It's doing this. Yeah, I know, but that's okay. That one's doing this. They're still going up at the end. All of these, as you spread this thing out, is going to do that. Let's just find out how it behaves. Let's find out what kind of an answer we're going to get. Well, let's try to look at it. I mean, we said how the thickness was it, and you know, whatever thickness it was, you got that for a thickness. There's there, and the R is here. I mean, this is not drawn to any good scale, guys. I'm not pretending that it is. But you're basically just going to start walking all the way out. There's symmetry everywhere. In the end, the E field is always and only straight up from the point under consideration. From any point under consideration on this surface that's infinitely big, infinitely wide, infinitely long, infinite radius, or close to that, or for practical purposes, very big, so we can use this approximation, this will work. Yeah, this will work. How are we going to do it now? I mean, how would you look at it? Well, we know there's a lot happening here. And I guess we could say, if you're going to look at the E field, let's take a look here. We got the D, we got the dq multiplied by dA on each side, sigma dA, which is sigma dA is 2 pi r dr. What's going on here? Yeah, what is the dq? Well, it depends what kind of area you want to talk about. I mean, at some point, I mean, if it's really, really a big surface, we can kind of use approximations for talking about what we're trying to say, guys. You could also kind of look at it and say, well, okay, what's dq? dq, what is sigma? So on and so forth. I don't know what you're going to pick. I mean, we could, we'll choose this as we go. I mean, we know dq is this. dq equals sigma dA. That's the same as that. Sort of a horse apiece, guys. The main thing is we have a lot of language that we understand and that we can use at our convenience. So we'll cross those bridges as we got to cross them. Looking at it, okay, let's take a snapshot of what the heck's going on here. I guess you could say gut feeling on this whole thing is we've got, and notice this is true of whatever height we're talking about under consideration. What height is this? You know, from what height is this, and what are we getting for an answer there at that particular point? So let's see exactly what we want to do here. You may want, just trying to use some of the language I used last time, guys, but I think we can transcend some of the limitations that we put on ourselves with maybe earlier language on this and just kind of say, okay, regardless of the language I'm using, can we make this thing work? Just trying to think of a height here. I mean, I could just put this as a height h, but I may not need to. I mean, let's just say this height is h from here to here, that point right there, and then we can kind of talk about it. If you have this, and we said we got all this business, I tell you what, there's got to be a shortcut here. Here's a cross section. Here's a cross section. That's a ring coming out. A ring coming out at you, or a ring going in. So it's, you know, whatever. Ring in, ring out. And I think it's just a bad idea to draw that, guys. But you know what I'm saying. There's a ring there, and there's a DQ associated with it. There's a small, you know, there's a lot of DQs actually. I mean, you can call this, you could call like this part right here, that's a DQ, and I can call this, that's another DQ. Here's a DQ. Here's a DQ, and here's another DQ. Here's a DQ, and here's another DQ, and they're opposite each other, and they all cancel. How about if you make the ring small enough, you call the whole thing? You call the whole thing one big DQ. You know everybody cancels. All you need to do is know the angle at which it's going and work your way out. basically what's happening, guys, is you got a point here. It's at a height, I don't know, we say a lot of stuff here. I guess call it H or A or, let's call it A. Let's call it A. I think I'm trying to remember the language, and yet at the same time, as I just said, it doesn't matter. Yet I'm making a bigger deal out of it than I should. Okay, that's it. Let's say that's A for height. And this is R for radius. And this is, again, now we're going to, you kind of look at it like this. Sigma over A, the whole thing 2 pi R. How about you just stay with this guy being A. I'm going to put an R. It's neither here nor there yet. R is a big radius, let's say, but you could call it anything you want. You can call it capital A. You can call it anything. I mean, call it omega if you want. But the reason I don't want to do that is I want to call this guy R. I want to call the height going up to here. The E field goes this way, and you get an answer. E field goes this way, and you get an answer. Yeah, you got to be careful though. Which answer counts? Only the portion. For all of these, we'll make all of them together. If it's a real thin strip, we'll make the whole thing dq. How do you want to do this? I mean, there's a lot of ways to do it. You could say, call that theta. Start at theta equals 0 and go toward theta getting real big until theta equals 90. I mean, if this thing spreads out forever, the theta gets bigger and bigger and bigger without really making it to 90, but getting as close to 90 as you want. I don't care about the stuff getting thrown. I care about that, and I care about that, and I'm going to add those, those come together. But I don't care about this guy, the E field going this way. Here's an E field for you, and then here's that. Here's an E, this guy, so this guy goes this way, E field here, and then there's this component. This guy goes this way. There's an E field here, and then there's that component. These always cancel. I just want these. Those are, whatever the size of the E field is, get the cosine of theta, and you're set. Okay, I agree. So what is all that about? I mean, how's that going to play out when you're actually doing this? You're going to look at it, and this is from this point right here, so it's from this point under consideration. You look at it and you say a lot of things. I mean, you say capital R squared equals small r squared plus a squared. This capital R changes. Yeah, so does small r. True. Is it true if you get the square root of that, r squared, a squared, square root of that? True. Is it true that the cosine of theta, is a over r? A divided by r. Yes. And what's that? Well, that r goes forever. I can write it in terms of this and this. It is A divided by r. So, yeah, true. Well, let's add them together. Let's add them all together and figure out what's going on here. Well, what do you mean? Well, there is a grand total of small dq's, Added together, they give you big dq, but it's still small. It's still infinitesimal. I mean, you can call these d small q, d small q, d small q, d small q, d small q. The whole thing is d capital Q. Yeah, and if this thing's narrow enough, it's tiny. So how are we going to do it? So we look at it, and we see what we can say. Everybody's got the basic argument that I'm trying to make here. Cosine theta equals all this. So let me see here. How are we going to do this? Well, what do you say you take, and you remember that you got K. Well, you got to be careful now. The entire ring, the entire infinitesimal ring is dq. KQ, or in this case, KDQ, that's your Q, it's dq now, over R squared. A is a constant. A is a constant. R is variable because you're going to be dealing with rings that are here as a ring, here is a ring, over here as a ring coming around. The ring comes all the way around, bam, goes in, goes there, and all are going to have a dq associated with it, some kind of a dq. Okay? So on and so forth. So what you have is k dq over r squared. What's r squared? R, the big R squared is small r squared plus the constant. The constant A. Yeah, this is crazy in its own right, I guess you could say. You could say, okay, it's as though the dq, which is the whole ring, the dq is the charges over the entire ring. The dq is found, all of the dq, the entire dq is all the charge on the ring. That's the dq. That's the dq. Okay. True. It's as though it's in one place only and it's firing up this way and you just want its projection right here. All the little guys contribute and make it as though it's one big E field. Yeah, but they all cancel out. So if you're going to do that one giant E field, yeah, it's as though it all originated here, just here. Don't worry about anything else, not even around. Fires all the way to here. And now please project it this way because they all canceled out. Times the cosine of theta, which is A over R squared A squared. Okay, guys, like I said, I'm going a little bit off script here, guys. Please be patient. I just think it's good. I think it's good for you to see it. I mean, you'll see it, and if you look at some of the other videos, you're going to see the same thing. Perhaps it's better in the other video, but at least I want to give you at least some feeling for it if you don't encounter the other video that was intended for another class, but being made available to everybody. Yeah, looks like this. Why don't you integrate that? Sure, I'm all for it. From where to where? Well, you start at the small r being 0, going all the way to infinity. 0 to infinity. I think it's going to get me there. So, looks pretty good. Looks pretty good, guys. Let's see if we can do it. Let's see if it actually works. I may have to change the battery here in a second, guys. I'll change the battery on this one real quick. Okay, thank you, folks. Let's look at that. Not sure what to erase, what not to erase. You know what it looks like. You know what to do. I think we're okay. We know a lot. All right, let's do the integral. Let's see where it goes. Let's talk. Let's draw a conclusion. We set at the height A. A lot here. Okay, that's fine if there's a lot there. Let's just keep talking. We're going to find the E field. We're not going to get overly concerned about it. We're just going to say this. Didn't we say dq? Didn't we say dq is sigma times 2 pi r dr? There's an A right here. There's an A right there, AK dq. dq was the sigma 2 pi r dr. We'll cross every bridge as we have to. This right here is to the 1 power, which is this entire thing taken to the 1/2 squared. It's to the 2 over 2 power. This is to the 1/2 power. This right here, the square root of this is just this to the 1/2 power. That's the same as taking the square root of this. If you get rid of that, you just take r squared plus a squared to the 1/2 power, and you got r squared plus a squared to the 1 power. When you multiply them, you add the exponents. 1 1/2 is 3/2. Wow, okay. It's not bad. We're almost there, believe it or not. There's an A, the height A, right? There's an A, there's a K, there's a sigma, wait a minute. There's an A, which is a constant, a K, which is a constant, a sigma, which is a constant, a 2, a constant, a pi, a constant. What's going on here? Tell you what, I'm going to leave the 2 in there for good reason. You got A, K. AK sigma pi and again I'm trying to remember some of the language, and at the end of the day we don't need to remember the language. We need to remember the technique to get to here. Why am I going there? Why am I doing that? Just look at that. Wait a minute. If u were equal to r squared plus a, r is a variable from 0 to infinity. A is a constant. If u is equal to that, du dr is 2r. du is 2r dr. There's your 2r dr. There's your 2r dr. And go there, get the answer. There's a lot you can do. There's a lot you can do. What is that? Let's just don't worry about the limits right now. Just worry about getting it. Look at the integral. This stuff's a constant, we know. This is your du. This is your du. Oh yeah? And that's your u, so the 3/2. Du, u to the 3/2. That's the same as u to the negative 3/2 du. Let's use the power rule. Add a positive 1 to that, you get negative 1/2. Let's see what we got here. You add negative, let's make sure I got it right. Yeah, I mean, it should be, let's just make sure here. Let's do the power rule. You add, here's the, we'll do the power rule. You add a positive 1 to negative 3/2, you get negative 1/2, right out here. And you put, you know, positive 1 times negative 3/2, you get negative 1/2 right here. Okay. And you get this. U to the negative 1/2 is 1 over u. 1 over u, you know, it's 1 over u to the 1/2. U to the negative 1/2 is 1 over u to the 1/2, which is this. Okay, sure. It comes out to that. So how are we going to do it? Well, okay, we're doing that, and this is, you know, you saw the process. We got it. Well, yeah, we do. Let's be careful. We got negative 1/2 times this times all these. AK sigma pi. AK sigma pi. Negative 1/2. We'll deal with it. I mean, I'll put the 1/2 is just divide by 2. I'll put, let's see what we can say here. Put the negative inside. Negative 1 over okay. 0 to infinity, or as the limit as it goes to infinity. Not being incredibly rigorous on this, guys, but we're, you know, we know enough. What do we got? Well, okay, I mean, this is it's not as challenging as you think it is. Throw a really big number, a really big positive number in here. Make the number go toward infinity. Well, if it's a really big number and you square it, it's huge. And you add a squared to it, it gets a little more huge. Well, if the number is really, really big and a is a constant, I can make r every bit as big as I want, and it's always going to transcend by far what a is and what a squared is. So it's approximately equal to r squared. If the number's huge, if the number's really huge and you square it and then add something to it, it's even more huge. When you square root it, you just get back to a number that's even it's a little bigger than the original huge number. Let's make a long story short. If you put a huge number in here and you square it, you get a very huge number. You add a squared, even more huge. You square root it, it's still a huge number. If you square root this quantity, it's bigger. The square root of r squared plus a squared is bigger than the square root of r squared. And the square root of r squared is just r. Yeah, but that r can be as big as you want it to be. can go toward infinity. What's negative 1 divided by something going toward infinity? It goes toward 0. That's out of the picture. That's 0. Put a 0 in here. For the 0. Put a 0 in here. 0. Plus a squared is a squared. Square root of a squared is a. This is negative 1 over a. Yeah, minus negative 1 over a, and that becomes positive. So it becomes positive a. On the bottom, a here, k sigma pi. Pretty fascinating. Okay. Put the infinity in here, something huge. Something huge squared is even more huge. Add a squared to it, it's even more huge than that. The square root of it is bigger than the huge thing squared, square rooted. So it's still a huge thing on the bottom. Negative 1 divided by something as huge as you want it to be goes towards 0. That's 0. Put a 0 in here for this one. 0 squared plus a squared is a squared. The square root of a squared is a minus negative 1 over a. Minus a negative 1 over a is 1 over a, and it's that. What's going on here? Well, isn't k the a cancels. The a cancels, that means the height doesn't matter. K is 1 over 4 pi epsilon naught. Sigma is sigma. Pi is pi. Forgive me, there was a 2 here too. There was a 2 right here. A, K, sigma, pi. There was a 2 here. And the A we got was that, so the 2 is here too. For some reason, guys, it's got to be something different. Oh, it's 1 over that. So it's 1 over the 2, guys. I'm sorry, when I was doing the integral here, that should have been a negative 2. So the negative 2 should be on top. Yeah. Oh, I'm sorry, guys. Let me just kind of show you that. Yeah, the negative 2 should have been on top. Everything else works. The basic dynamic of what you got to do is this. The main integral of what you got to do is that. You remember when we had u to the negative a half du, we had u to the negative 3 halves du, that integral. And we said you add 1, you know, how does that work? You know, it works like this. If you're integrating, you know, you guys remember if we're integrating u to the n, that's 1 over n plus 1 u to the n plus 1. So that's the move I failed to make here, guys. So you take this, which is your n, so to speak. That's the n. And this is your n. And if that's the n, you add 1. If this is the n, you add 1 to negative 3 halves, and you get negative 1 half. Then you go 1 over negative a half. So you add 1, you add positive 1 to, you know, just like we did here. Same thing here. You add You add a positive 1 to negative 3/2, and you get negative 1/2 for the exponent. And you go 1 over that negative 1/2, and you end up getting this right here is negative 2 u to the negative 1/2. This u to the negative 1/2 is this. That's the u to the negative 1/2. The negative 2 is what I failed to see the first time, and there's your there's your negative 2, and that should have been there. That one's on me. Well, yeah, absolutely. That's the way you're going to do it. So if you look at it, negative 2 u to the negative 2 times u to the negative 1/2. Well, here's your negative 2 times u to the negative 1/2. To the negative 1/2 means 1 over the square root of the quantity u, and u is r squared plus a squared. The negative 2 is here. You can write negative 2 here, and you just get rid of this guy here. You know, you make that a positive 1 and put your negative 2 here, or take the negative from the negative 2 and put it right here. All right. Sorry about that, guys. A little bit of a mess, but there it is. Now, this shouldn't be too bad. Okay, well, all right, you heard the song and dance. Here we go. We drew the conclusions that we drew. We got E. We got E equals 2A K sigma pi. We saw this song and dance. It was a long one, but we saw it. We saw how it ended up. Two A K sigma pi. 2A K sigma pi. This song and dance, just by itself, right here, was A. There's your answer, guys. There's got to be an easier way to look at it. Yeah, there's constants all over the place. The A cancels out. The A cancels out. We got 2. We've got K, which is 1 over 4 pi epsilon naught. We've got sigma. And we got pi. Yeah? Let's talk. Yeah, let's talk a little bit. The 2 and the 4 cancel. The pi and the pi cancel. The 2 and the 4 cancel. The 2 and the 4 cancel, leaving us a 2 on the bottom. The pi and the pi cancel, for real. You got this. Nowhere do we see the A, the height of A. Somehow, with the beauty of the mathematics, it doesn't matter how high above this infinite sheet that you are. You could be right next to it, a millimeter away from it, or you could be a billion miles away from it. If you start in one place, you could be 0.1, you could be 1 millimeter away from the surface, and the E field pointing upward, hitting you there, is the same amount of E field hitting you as if you were 1 billion miles away. A could be 1 billion miles away from the surface. And the E field at that point, 1 billion miles away from the surface, is the same strength and direction E field as it would be for the test particle being 0.1 millimeter away from the surface. At all points, it's a constant E field, perpendicular to the plane of the surface. That's huge. It's huge, and that's the answer. Wait a minute, what's going on here? That's huge, and not only is it huge, it tells us some other stuff. Can I ask you another question? What if it's a capacitor, also infinitely long, and separated from the other one by a distance d, small d? But it's not a positively charged surface. The sigma is not positively charged. For the capacitor, one of the plates is positively charged, and the other one has an equal and opposite charge, which is a negative charge. What happens then? Well, then the positive test charge is expelled this way. The positive test charge is expelled this way and drawn this way. I wish I could have made it with the same amount. So wait a minute, if it's a parallel plate capacitor, you guys, if it's a parallel plate capacitor, that's for one of them. Does everybody understand? Yeah, if it was positive, wherever it is, this guy's right here is experiencing an E field E, a positive, here's your test charge, positive, it's being expelled going upward. Positive test charge experiencing a repulsive force here, E field therefore is this. This guy, it's got all the same numbers exactly. Same infinite dimensions, same mathematics goes on, only it draws. The E field draws inward, but everybody still cancels out. The positive test charge here is expelled upward. The positive test charge here is drawn upward. The same E. I will do the same exact integral with the negatively charged plate. All the mathematics is identical. You say, well, yeah, which way direction is it going? It's not expelling it. If they were both positively charged, then the net E field would be 0, I guess you could argue, right? Because I'm pushing this way, the other's pushing the other way. It's a pushing war or a pulling war. They're both pulling the exact same amount and nothing else, or they're both pushing the exact same amount and nothing else. Yeah, I guess I'd say it's 0, right? We'd look at it, yeah, we'd say it's 0. But here, it's being pushed and drawn with the same exact E field strength. What does that mean? What is the total E field? It's sigma over 2 epsilon naught plus sigma over 2 epsilon naught. It's sigma over epsilon naught. I said that last time. What's sigma? Sigma is Q over A. Yeah, sigma is Q over A. Sigma is Q over A. Here's your epsilon naught. The E field for the capacitor, the E field between the plates, is given by this. Really? The potential difference, we'll call it V. Isn't Q times V the work? Isn't Q times E, force, times distance is Q, put a small q here, positive test charge. Q times E is force times D is work. Q times V is work. V equals E times D. This is some of the stuff we were talking about. V or delta V equals E times D. V or delta V or delta V is E times D. E times D is, well, E times D is Q over A epsilon naught. Q, D over A epsilon. Interesting. Interesting. It's the capacitance. Capacitance is Q divided by V. Capacitance is Q divided by V. Yeah, Q was the total charge. Is this infinitely big? Well, let's terminate it somewhere, but it's it's huge enough, it acts like it's infinitely big. So we'll give it a particular Q that has a particular value, that's some value, but it's huge. Q, capital Q times D over A epsilon naught. Q over V. What do we got? C is C. The Q's cancel. The A epsilon naught comes on top. The Q's cancel. The Q's cancel. A epsilon naught over D. We've seen that. It's where it's coming from, guys. I couldn't resist going through it again. Again, I've done this in another place, and I've made the notes available to my non-calculus based class. But I also make it available. It's also available to anybody who's going to look at it, and it's available again here. Okay, so this is C equals A epsilon naught over D, or A, epsilon naught A over D. Usually they put the epsilon in front. That's kind of the convention on the whole process. Let's look at it. Yeah, you got epsilon naught A over D. That's not a big deal, guys. I mean, that's definitely a horse apiece on that, but okay. Well, all right. We've been through enough of this. I think we can get it. I think we know how to do it now. Now, what they're trying to say is, take this, take all the argument that they're trying to give you on this whole process, and say what you can say. I mean, say what you can say about it. So let's see what we can say. Let me just start writing it. I think we got all the notes we need on that. Let me leave the picture up there. Pretty fascinating stuff. It's a little more, obviously it's more lengthy. I mean, than other approaches. A little more of a, I think much more of a gut feeling in some regards if it can be done. You're confirming the brilliant work that Gauss did, and you're doing it in a very, like I said, I think very intuitive manner. There's a lot of work to it, obviously. Frequently, just to see it on your own and explain it to yourself is going to be easier than a teacher trying to explain it to you. I guess you could say there's somewhat less that anybody has to do, teacher or student, when they're trying to explain it just to themselves. But to try to articulate the stuff is a little messy sometimes, guys, but I think well worth it. Look at it. Work it on your own, too. See what we can say on this stuff. Okay. We got a lot. We said a lot in the beginning of this problem, and let's just keep talking about it. Make your expression here. Find an expression for the electric field between two conductors. Yeah, I mean, you kind of, the way you want to say it, the electric field, we know the capacitance was with the electric field. You're going to get stuff that's going to look pretty similar. So let's take a look at it, guys. For some reason here, I thought I saw something else. Okay, no, all right. So we did a lot. Just start writing a bunch of stuff here on this. You'll see it in the notes too. So. All right, guys, much of the song and dance we've done. For the heck of it, let's put it here. We can say there is an equivalent, we can say, sort of charge opposing. In a sense, you could say it's negative. It's opposing what was going on initially, and we talked about that. Follow through pretty good. Well, okay, we've said a lot. We said what the Q free was, so all this other stuff. We talked about E total. After we did all this earlier business. Again, there's just not as much of the positive charge, effectively speaking, how you would visualize that in a Gaussian surface, because the E field is indicating that effectively the positive charge under consideration to do this is somewhere else. Is in a sense there's more to this, and there's just not the dielectric is essentially creating this issue. Q free equals kappa. All right, let's see what we can do here, guys. We did a lot of stuff. There's a lot here. You can say, basically, you can go from here. I do something a little bit different in the notes, guys, but I think given all the stuff that we've said, I think we can kind of go a little bit faster at this point. Q free is going to be, there's going to be some effective sigma times A. Now, we've been there. We've done that. Now, in this case, the R squareds are the big one. Here, I'm changing. We're talking a different language here a little bit. Q over pi R squared times A will give you the free. What does that mean? Well, if that's this, epsilon kappa A, regarding that, let's kind of see here. It's pretty basic stuff. Once you get comfortable with this, you say effectively the charge is not the same, so something's up. Okay, then go ahead. If that's the case, you know, how would that play? You know, how would that play out? So it's, okay, let's just keep going on this. So we look at this. Right? Right. Right, because the in is smaller, the in is less, the in comes out less. This kappa guarantees you're getting the in, because you're taking the Q free and dividing it like that. Well, take the a's out of there, pi r squared, put it on the bottom, and what do you got? I just said E, we didn't put the total on there, but they mean total in this case. You got Q over epsilon naught kappa pi r squared. All right, good deal. Yeah, I mean, looks a lot like what we said earlier. Didn't we, when we did the, unfortunately I've erased it, of course, but we had, what was going on here? Didn't we, wasn't it coming out to, wasn't that E field that we discovered, you know? Wasn't that E field that we discovered, wasn't it Q over epsilon naught times A? You put the kappa in there because you gotta divide by kappa. That's the free guy. It's got to be the free. It's got to be the free. If you multiply by D on each side, you got Q over kappa true. The capacitance is Q over kappa, right? That's the Q, right? Over Q over kappa D over epsilon naught A. Well, that's gone. C becomes epsilon naught A epsilon naught A over D. You know, for the capacitor. So you are, for all things considered on that, you could look at it, the capacitance of the new situation there. For some reason, I think there's got to be a kappa in there too, but how are you going to get that kappa? You're going to have Q here over kappa, right, E. The kappa comes up over Q. There's different arguments. For now, let's not, I'm not going to dwell on this right now, given all, given I'm kind of doing this cold, but I do want to say this. You're seeing the exact same format, ladies and gentlemen, playing out. You know, if the voltage is that, it's less, but you were to have the same amount of, see, you'd have, the voltage would be less, but you'd have the same amount of charge. Why are you getting the same amount of charge as you did earlier if the voltage is less? Because for less voltage, you get the same amount of charge. And that would get you the K. And that would give you the kappa. That would give you the kappa. Again, the big story here, guys, C equals, even if you get rid of the kappa, C equals epsilon naught A over D. Look at how all the mathematics has a consistency to it. Typically, I'm not asking people to derive this stuff, but it's good to look at this stuff and have an idea. For number 62, an air-filled parallel plate capacitor is charged to a certain potential difference. An air-filled parallel plate capacitor is charged to a certain potential difference. A dielectric is then inserted in the capacitor to completely fill the space between the plates. Then the charge on the plates is increased by a factor of 3 to restore the original potential difference. Determine the dielectric constant. The 3 gave it away. Well, look at it again. It kind of gave the answer of 3 already. An air-filled parallel plate capacitor is charged to a certain potential difference, period. A dielectric is then inserted in the parallel plate capacitor to completely fill the space between the plates. Then the charge on the plates is increased by a factor of 3 to restore the original potential difference. Determine the electric constant. You got it right there. By a factor of 3 tells you what kappa is. Here's why. We're basically looking at the C air, the C sub air we'll call C. The C dielectric we'll call kappa C. Sounds good. Fair enough. Kappa C would be kappa times Q. Multiply both sides of this equation by kappa. Kappa C equals 3 Q over V. They said they tripled the charge to get the potential that was going on earlier. That was going on with this one. You had to get triple the charge for that to happen. Oh, really? If you had to go triple the charge for that to happen, kappa does it, because that's kappa Q. That's the kappa Q. That was 62. 83. A capacitor, C sub 1, has potential difference V and stores energy, U sub 1. It is then connected without loss of charge in parallel with a second capacitor, C sub 2, that was initially uncharged. A. Find an expression for the energy U sub 2 stored in C sub 2 in terms of C sub 1, C sub 2, and U sub 1. B. Show that U sub 2 is a maximum when C1 equals C2. Hint, and it's a hint, consider the derivative of U sub 2 as a function of the ratio x equals C1 over C2. Okay, this is one of those easier done than said ones, guys. Well, I mean, look, this capacitor C1 has a potential difference V and it stores energy U1. It is then somehow connected without any loss of charge, and it's put in parallel with a second capacitor C sub 2. If it's put in parallel with a second capacitor C sub 2, they are going to have the same potential difference across. C1 is going to have the same potential difference across its plates as C2 has, if they are in parallel. If they are in series, they're both going to have the same amount of charge. This is not the case. They're not going to necessarily have the same amount of charge, but they're going to have the same potential. Each one, the potential difference associated with C1 is going to be the same as the potential difference associated with C2. Find an expression for U sub 2, the energy U sub 2 stored in C sub 2 in terms of C1, C2, and U1. Then show that U2 is a maximum when C1 equals C2, and they got a couple hints for us to do that. Okay, let's get down to business. All right. Look, we're talking about these guys being in parallel, right? If we're talking about them being in parallel, we know the equivalent capacitance of the two is going to be C1 plus C2. That's if they're in parallel. We know that U1, I'm going a little bit different than what I showed. U1 is going to be 1/2 true. The total charge that was initially present will remain after all is said and done. Q total is Q, and whatever the voltage was, whatever the potential difference was across the plates times the capacitance told you what kind of Q you're talking about. True. We can also say that that same Q is attained by an equivalent capacitance, whatever it may happen to be, and some equivalent voltage. I mean, they're going to have the same potential difference across their plates. We just don't know quite what it is, but we will know that it forms one big capacitor, an equivalent capacitor, and the same Q will be across. The same Q will be across that. So all together, I mean, so it's the way you got to look at it is what it is. VEQ equals, well, I'll tell you what the equivalent capacitance has got to be. It's right here. VEQ is going to be Q divided by CEQ. Wait a minute. Didn't we say CEQ was this plus this? Yes. True. Didn't we say that Q, at least initially, was what the initial one was, and it was just a V? C1V was the Q. Okay, we're not done. Certainly not done, but at least we're walking in a decent direction here, guys. We got an idea what's happening here. What's going on here? Well, they want U2 as an expression. What's going on? I mean, well, I'll tell you what. U2 is going to be 1/2 whatever C2 is times the voltage equivalent that you eventually attained when they reached some kind of quote-unquote equilibrium. What's going on? It's 1/2 C2 rather. VEQ is C1V yeah, it's quite the mess, but there it is. Is there a way we can look into this thing and make some sense out of it? Yeah, I mean, you remember let's try to get everything, you know, just try to talk in terms of the language they want us to speak. U1 is 1/2 C1 V squared, the original V squared. What's going on here? Well, I'm trying to just 1/2 C1 V squared. Okay. I tell you what do you say? Number of ways to go here. I don't like the way I calculate. I mean, this is correct what I wrote. I just rather give you a better gut feeling for what's happening here. Tell you what. Do you agree that 1/2 C1 V squared is U1? Okay. Tell you what. Here's C2. Here's C1. Let me put the half. Got to talk to you. Why don't you square this quantity? I know this bottom thing gets squared too. Why don't you square this quantity? It's C1 squared V squared. C1 squared, pull a C1 out of there and bring a half in there. Pull a C1, this is C1 squared V squared. Pull a C1 out of here, keep one of the C1s in there, bring a half in there. The V squared is here. We got that. And underneath, we got, I think I did it essentially the same way. I just didn't like the way I'm looking at my notes. I'm not crazy about my notes. All right, you got that. That'll work. Look at it, be careful. It's not too bad. Just be careful. Obviously, the careless mistakes are easy to make, that's for sure. C2C1 or C1C2, 1/2 C1 V squared is U1, and this guy is C1 plus C2 squared. That's the end of the story on that part. You got it in terms of C1, C2, and U1. Good enough. Good enough. And that's A. That's A. A is saying what? Find it, find an expression for U sub 2 stored in C2. I'm sorry. Find an expression for the energy U2 stored in C2 in terms of C1, C2, and U1. We did it. We got it. B, show that U2 is a maximum when C1 equals C2. Consider the derivative of U2 as a function of the ratio x equals C1 over C2. This is a good one. All right, this is A. Great problem. I mean, this is excellent. You got that one right there. Now what? When is it at its maximum in terms of C1? We got to find that C1 and C2 have to equal each other for that to happen. It's a fascinating point. When are they going to be? When is it going to be at its maximum? U1 is a constant because it was something that was initially occurring. It was something initially occurring, so we've used it as a reference frame. So it remains a constant. It was a constant, and it remains a constant. It was something initially occurring, and it's being used as a reference frame. This is C1, C2. This is the quantity C1 plus C2 squared. There's a lot of debates can take place vis-a-vis all this, I guess. Yeah, you can do a lot. Here's the way I kind of did it. I said or they said, and I agree, let x equal C1 over C2. And do you mind if we take U sub 2, and I'll tell you what do you say we multiply U sub 2? No, let's not multiply. Let's multiply U sub 2 by 1. And let's multiply this by 1. But here's the 1 that we're going to use. The quantity 1 over C1, C2 over the quantity 1 over C1, C2. The special one is 1 over the product. Special one is 1 over the product, C1, C2, over 1 over the product, C1, C2. Let's take the C1, C2 right here. Let's C1 plus C2, let's take it all the way out. C1 squared plus 2C1, C2 plus C2 squared. Yeah, okay, let's go. What happens? Yeah, this is 1 over the product C1, C2 times the product C1, C2. Gets out of there. This goes here, and let's kind of deal with it. You're talking about C1, C2. C1, C2, that's just 2. That's kind of neat. Yeah, I mean C2 over C1. Rather interesting. There's some symmetry here. What's going on? Well, didn't we say let's use X use the x is equal to that. C1 over C2, huh? Yeah, U1's a constant, so we're not really worried about it. So what we have here okay, we know what to do. We feel okay. What's going on here? Well, U2 is a variable. U1's a constant. So, okay, keep it in mind. It's a constant. That's nice. These are variable. C1 over C2 is X. 2 is 2. C2 over C1 is the reciprocal of C1 over C2. So it's this. Write that a bunch of ways, guys, but they're all going to mean the same thing. U2 is a maximum. Guys, this is a constant. This ain't changing. This is not going to mess with us. Constant. If this is a minimum, we're set. It doesn't become a minimum as easy as you think it does, you know. But let's look at it. We got to have it be a minimum. You can't have it be 0. If it somehow went to 0, this would blow up on us. Let's see what's going to be for the minimum there. There are a lot of ways to go here, guys. The 2's in here, right? Yeah, true. Whatever. You can put it in there or not put it in there. It doesn't matter. Take the function 2 plus 1 over x plus x. The 2 doesn't really matter. This has got to be a minimum because 2 doesn't change either. We're not going to worry about that. I didn't worry, you know, I kind of did it, got rid of the 2, and it was a little easier to deal with, but that's neither here nor there. Get d dx on that and set it equal to 0. What is d dx of this? Well, derivative of 2 with respect to x is 0. Derivative of x to the negative 1 is negative 1 x to the half. I'm sorry, it's negative 1. The derivative of x to the negative 1 is negative 1 x to the negative 2, which is this. And the derivative of x is 1. That equals 0. Add a positive 1 over x squared on each side. You get 1 equals 1 over x squared. You want it to be 0. It's a bit debatable now that I really want it to be 0. Yeah, I guess I want it to be the minimum thing it could be. On the max side, I could also say I flip this upside down, and I want it to be the maximum number it could be. And I could do that derivative and set it equal to 0. So that you know, I could get you know how that plays out. How are you going to get the biggest ratio regarding something like that? So you could say, okay, that's got to be a minimum. Yeah, okay, the derivative of it has to be equal to 0. Hopefully the ratio itself is not equal to 0. It's not going to be. Multiply by x squared on each side. Multiply by x squared on each side. X equals plus or minus 1. That's absurd to consider the minus. X equals 1. C1 over C2 equals 1. When C1 equals C2, there's your min. There's your min. No such thing as a max on this. It's not bounded on the bottom. So don't worry that you're making a mistake here. If x goes toward infinity, man, x goes toward infinity is what it is. If x goes toward infinity, it gets as big as you need it to be. So there's no biggest value. There's a smallest value. And luckily, if x equals 1, you're not in big trouble. You're okay. If x equals 1, you've got, if x equals 1, 1 over x, x equals 1. 1 over 1 is 1. That's 1 right here. 1 and 1, 2, and 2 is 4. U1 over 4 is equal to U2. U1 is 4 times what U2 is, or U2 is 4 times smaller. But that would be the biggest. Because now let's see what they're saying here. They're saying, show that U2 is a maximum. U2 would be at its maximum when it's 1/4 of the size. U2 is at its maximum when it's 1/4 the size of U1. And that will happen. That'll happen when the C's are equal. With C1 and C1 equals C2. Pretty fascinating stuff, guys. How they do the mathematics. Pretty fascinating stuff. That was 83. Look at 86. The 1 centimeter gap between the horizontal plates of an air-filled 44.0 microfarad parallel plate capacitor is slowly filled with peanut oil. Kappa equals 3.0, all of it. How does the capacitance of the capacitor change as a function of the height h of the oil that fills the gap between the plates? Well, guys, we're basically told this for problem number 86. For problem number 86, we're told that induced dipole layer occurs as gap is partially filled at any particular time. So there's a K up, there's a distance D between the plates. We'll call the distance D between the plates D, and there's a K down, and that's H is the height of the peanut oil. It is as though these two C up and C down are in series, and then from there we can kind of deal with what we have to do. All right, so all right, so there's kind of a dipole going on in that regard, and it's fixed in such a way they become like parallel, they become like two capacitors that are in series, and we got to start doing some stuff regarding that. So we're told that the induced dipole layer, we're told that there's an induced dipole layer, we're told that there is an induced dipole layer, and it occurs as the gap is partially filled at any particular time. So what's going on here? There's an up, there's a down. From the bottom part, you're talking about the peanut oil. From the top part, you're talking about it still being air filled. it is as though these two, you know, are in series, as we just said, you guys. So there's stuff we can kind of look at. If we are going to go down that road, there's an up, there's a down, and the up is the air filled. The bottom is associated with the peanut oil that is filling in from the lower part of this arrangement. So somehow it's put together that the peanut oil is not getting spilled out. It just rises to a height h. Well, the distance between the two capacitor plates before all this happened was d. And when it rises, the peanut oil rises to h, you got a capacitor associated with a separation h, and you got the other capacitor associated with the difference between d and h, which is d minus h. It's kind of the way they're trying to do this, guys. So they say a lot of stuff here. I mean, they say that, so how are you going to write this? Well, the CEQ equals capital or lowercase, you know, down. It doesn't really matter. That's okay. What's going on? Well, you got to remember, the C associated with the upper part is all air. And all air, well, how much is air if you got a height of h of peanut oil? Only that much thickness of air if part of the D thickness, H part of it is filled with the peanut oil, whereas D was the entire thing. Yeah, but H of it is now taken up with the oil. So this is associated with the capacitance associated just with air, and the down is, now this E, this epsilon, this epsilon sub naught times A over H, I mean, epsilon sub naught times A over D, wow, we've gone into that quite a bit, right, already. So we're looking at this. So this is what you're going to use. You're going to put this and this. The up is that one. The down is that one. That one. Not the stuff above it, just, you know, the C up, the C down. Then afterwards, you know, you got this. You got to tinker with that. You got to make it work. And we said they're in series. Well, wait a minute. The down had 3 because the kappa associated with the peanut oil is, the kappa is 3. So we got that. Well, you got it. I mean, let's see where it's going to go, how this whole thing's going to play out. So one over C up. Okay. 1 over C up is the reciprocal of C up. The reciprocal of C up one over C down is the reciprocal of C down, which is H True. You know, look at it. Look at it carefully. Tell you what, you got 3 epsilon naught A, epsilon naught A. What do you see multiplied by a special 1 called 3 over 3? And now you got a common denominator. CEQ equals 1. What do we got? Well, we got 3 epsilon naught A I don't know. Let's see what we got. 3 times D is 3D. 3 times H is 3H. 3D, 3 times the quantity D minus H is 3D minus 3H plus 1H is 3D plus a negative 2H or minus 2H. All right, doesn't look great, but we know how to do it. 1 over all of that is the reciprocal of all of that. One over this ratio is the reciprocal of that ratio. Notice it's of the form epsilon naught A over some distance. It's a complicated looking distance, but it's in the terms of distance somehow, or some kind of manifestation of units of distance. Notice the epsilon naught A over some kind of D, yeah, it's of that form. We got, I don't know, there's saying a whole bunch of stuff here. I think they wanted to write it. How does the capacitor change as a function of the height h? I mean, you can argue a whole bunch of things here, guys. D was a constant. 3's a constant, 3's a constant, epsilon naught's a constant. The A is a constant. The plate area isn't changing. 3 a constant. D's a constant. Here's the H. Yeah, you could write it like that. They kind of make it look a little nicer by doing some stuff here. What they do is you could take this and there's just a lot of ways to go, guys. You could take epsilon naught A and introduce division by D. Yeah, if you do that, you better introduce multiplication by D. That's 3D. You took epsilon naught A. You took epsilon naught A. Epsilon naught A you took out of there. Then you introduce division by A, but then you introduce multiplication by D. True. In here, you can divide the top by 3D, divide the bottom by 3D. And they think that looks a little better, and they're probably right. I mean, it's arguable how you can go about it, what they'll allow. Multiply this factor, which is made of this ratio, multiply this factor by 1 over 3D multiply by the ratio 1 over 3D divided by 1 over 3D. 1 over 3D, so you just go 1 over 3D times 1 over 3D. Yeah, if you're that's 1. Multiply by 1. The 3D gets you a 1. The 3D goes in here. There's some interesting things that happen. It really makes it look like the old stuff that we've done. Somewhat old stuff, so to speak. It's a little, yeah, you can argue that it's easier to look at than the other one. The other one was certainly a function of x, of h rather. What did we do here? 2h over 3d. D is a constant. Later on, I think we plugged in a lot of ways to write it, guys. I mean, but you can plug in, there it is. I mean, that's the hardest part. Now you plug in the values. That's the bread and butter right there, guys. That's the bread and butter. You got it to here. You can calculate it the way you want to calculate it. They're telling us D is 1 centimeter. So you can make 1 centimeter is 0.01 meters. H is, you know, whatever you're going to have there for H. Whatever you're going to put in there. Epsilon naught A over D. I think they were telling us the capacitance in vacuum or in air, the epsilon naught AD, that's in air, and now you can keep it in terms of air. That was the big thing. You were able to take the 44 microfarads, which is that. That's the 44 microfarads. And then the rest gets you out of the woods. You got 1, you've got 2, H, and you've got 3 times 0.01 meters or 1 centimeter. Make sure you convert everybody to the MKS system of units to do it, but that's the argument. That's the argument. And they might have shown it just like that as well and not gone into more specifics on it. Let's just have a look. Maybe not. No, that was it. That was about it. That was about it. Okay. Yeah, so that can be written a bunch of, the big thing, guys, is this. Bam. You get it to this. The epsilon naught A over D, that is the capacitance in the absence of any dielectric. Epsilon naught A over D, epsilon naught A over D is the capacitance in the absence of any dielectric. And they gave us data pertaining to that. Wow, you got it here. You put the data they give you right here. In place of here, you put this. That's the data they gave you. You got everything else. They gave you this. Now from here, you can find out what's going on with H. What kind of capacitance you're getting as the oil is filling up. Okay. Let's do the last problem. '88, a parallel plate capacitor has square plates of side S equals 2.5 centimeters and plate separation of D equals 2.5 millimeters. The capacitor is charged by a battery to a charge Q equals 4 microcoulombs, after which the battery is disconnected. Okay. A porcelain dielectric, kappa equals 6.5, is then inserted. A distance Y equals 1.00 centimeters into the capacitor. Hint, consider the system as 2 capacitors connected in parallel. A, what is the effective capacitance? Now they got ABC on this one. What is the effective capacitance of this capacitor? How much energy is stored in the capacitor? What is the magnitude and direction of the force exerted on the dielectric by the plates of the capacitor? That's a great, just tremendous problem here, guys. All right, let me do this. Let me just take a little break, and I will come back and we'll just finish this last problem. Okay, guys, let's finish this up. From chapter 27, problem number 88. Essentially, they are talking about a parallel plate capacitor, and you're inserting a dielectric only partially into the entire space that's there. As far as the width of the space, the dielectric will fit from positive plate to negative plate completely. But what's going on here is you're bringing, this is the dielectric, you're bringing this in to the space, but not entirely into the space. This is S, distance S, this is distance Y, which is smaller, this is distance D, this is the positively charged capacitor plate, the negatively charged capacitor plate. There's a dielectric, that's the dielectric, and its dielectric constant is kappa. And they're saying, working with that, let's see what we can say about it. Well, they're saying a parallel plate capacitor has square plates of side S equals 2.5 centimeters and plate separation D equals 2.50 millimeters. So it's 2.50 centimeters for the square plates as far as their sides. The sides are 2.50 centimeters and the plate separation is 2.50 millimeters. The capacitor is charged by a battery to a charge Q equals 4 microcoulombs. So positive 4 microcoulombs on the positive plate and negative 4 microcoulombs on the negative plate. After which the battery is disconnected. A porcelain dielectric kappa equals 6.5 is then inserted a distance Y equals 1.00 centimeters into the capacitor. Remember, the capacitor has the total length of a side, and that's 2.5 centimeters. This is brought in not to the halfway point, which would be 1.25 centimeters, but only 1 centimeter. So it's brought in 40% of the total length. 1 divided by 2.5 is 0.4. So, well, consider the system as two capacitors connected in parallel. That's a hint that they give us. A, what is the effective capacitance of this capacitor? That's A. B, how much energy is stored in the capacitor in this system equivalent? What is the magnitude and direction of the force exerted on the dielectric by the plates of the capacitor? What's going on? What's going on with onto the dielectric vis-a-vis this whole situation? Okay, let's deal with it as best we can. Well, here's, we've said a lot of this, so let's just write it down. Since they're parallel with one another, we got, go about this a bunch of ways, I guess you could say. We got C1 is equal to kappa epsilon naught S times Y. What's S times Y, you guys? What happens here is S is this length, Y is here. A lot of ways you can actually say it. Because they're square, what is the dimensions of this? Well, this has got a height this much and a width of S going into the board. So Y times S is the area. Kappa epsilon naught times the area, kappa epsilon naught times the area over D, you got this. Well, if you plug in all that they've given us, And I've got that'll scroll at the end of the whole thing. You just plug in what they've given us, stay with the MKS system of units, and then you'll get 5.75 picofarads. It's probably a little easier to visualize that way. With C2, you're going to do the same thing. It's the same now. With the C2, now C1 was the lower part with the dielectric. This one does not have the dielectric, so kappa's 1. So it's epsilon naught. How much area is there? On a plate, just one plate now, right? You got Y here and S that way for this, what was going on here for its area of plate. Area of plate here is S minus Y times S. So the quantity S minus Y times S, or S times the quantity S minus Y. Plug in all the appropriate values there. So this is the air-filled portion. This is the air-filled portion, and you're going to get an answer. And this was the dielectric-filled portion, and you got an answer here. All right, so you got this. You plug in all the appropriate results. You get 1.33 times 10 to the negative 12. 1.33 times 10 to the negative 12, which is the same as 1.33 picofarads. This was 5.75 times 10 to the negative 12, and that was, so 5.75 times 10 to the negative 12, 1.33 times 10 to the negative 12. It's a little easier to visualize if you go like this. That's up to the person when they're doing it. We said they're in parallel. Well, that makes it pretty easy. That makes it easier. Equivalent capacitance, just call it C, since I've been calling C1, C2. So C is the same as C equivalent, so we'll use the language as we need to use the language, I guess you could say. C1 plus C2, good enough. You add it together, and you get, you're looking at it, you got 7.08 and that's the situation there. So there's a lot of ways. Okay, well, we said what we said. We got the answer for this one. They wanted the equivalent capacitance. We just got it. So another way to write it, yeah. I mean, the way to write it is symbolically in a more strict symbolic fashion without really putting the standard numbers that we're used to. Explicit numeric notation in there and just use the letters. What are we talking about? We're talking about you're taking this and you're adding it with this. Well, there's a common denominator at least. That makes it reasonable to look at, I guess. There's a common denominator. That's D. There's a whole lot of other stuff going on. There's an epsilon naught. There's an S. There's a lot there. So when you add them, you get an epsilon naught, an S, a D, an epsilon naught, an S, a D. Yeah, we had the D on the bottom. We had D on the bottom, epsilon naught S on top, epsilon naught S on top, and then we got the Y. Oh, this is pretty fascinating in its own right, isn't it? We've got that's the S, right? Okay, yeah, right. What am I talking about here? We've got the Y and we got the S minus Y. Yeah, there's a K there, guys. So there's the kappa Y plus S minus Y, which is, so kappa Y plus S minus Y is kappa minus 1 times Y. Right, I mean, and the other one was just the S, and you got the S right there. So the S can go in front. I have it. All right, wheel and deal a little bit with that, and you get what you're going to get. So let's see what we got here. Let's kind of go there with that. So at the end of the day, this is the equivalent capacitance in symbolic form. You know, there's got to be something that can be said here regarding this. So let's have a look. I mean, let's stay with this for now. Correct. And now they're saying, okay, well, tell me what is, you know, we gave the answer there, you know, what is the effective capacitance of this capacitor? This is the symbolic answer of the effective capacitance of the capacitor. And this is the literal answer with the numbers that they've given us for A. Let me use the symbolic answer for the capacitance of this parallel plate capacitor, which effectively it becomes. And let me say for B, they're saying how much energy is stored in the capacitor. Well, there's a lot of ways that can be written. They gave you the charge Q. You know, there's a number of ways to go, guys. You can crunch a lot of the data that you have and probably be okay. Let me see. Okay, the way I had gone about it, it's correct. Not the only way to go about it, but depends what kind of numbers you can, you know, what you have with the data that you have, what kind of numbers can you crunch. We know that's true. We know that's this. We know that's Q squared on top. We got it. What's the C? The C, this guy, with the C, the D flips up and these guys stay down. And you got epsilon naught S times S well, yeah, I mean, it's not. Looks good. I mean, it looks good. Plug in all the values that they've given us. And when we do so, that's what's stored. There's a number of ways to finish that off too, guys. But we got this. Okay. Well, I mean, that's how much energy stored as is. I think there's a lot you could say here on this whole thing. What are the magnitude and direction of the force? What are the magnitude and direction of the force exerted on the dielectric by the plates of the capacitor? You know, while this porcelain dielectric is inserted into the capacitor, what's going on? Well, what was happening before? What was the amount of energy stored? The fact that, I want to kind of explore something on this one. This is what we got for the U here. What would the U have been? What would the U have been before you put the dielectric in there? And, if that's the case, what would it have been? That's an interesting point. Well, what it would have been was that's the after, I guess we'd say for the before. Initial situation, just for the sake of looking at it, I think. The initial situation is going to be 1/2, and it's everything we had, guys. It's just not going to be, it's not going to be this funny business here. What it's going to be is, it's going to be, it's simply going to be without the K there, K1, it's just going to be the S squared. So it's going to be epsilon naught on the bottom there. It's going to be epsilon naught S squared on the bottom and the D on top. Epsilon naught S squared. That's the area. Epsilon naught A over D. And yeah, that's the capacitance. I'm going to divide by that capacitance right here. I'm going to go Q squared yeah, the capacitance is epsilon naught S squared over D. So Q squared divided by the capacitance. The capacitance is epsilon naught S squared over D. So when you're dividing by the capacitance, bam, that epsilon naught S squared over D flips and you get all this. Just for the record, I mean, what's going on here? Where's that going? Vis-a-vis that. What was it initially and what was it afterward that was stored? Just so we can comment on some stuff later on, I guess you could say. Well, let us see what we can say then on this, guys. I got to try to make it somewhat, hopefully somewhat easier. And as luck would have it, I might not even have a calculator here. We can kind of view the whole thing. This is a bigger number on the bottom. I unfortunately don't have for some reason I don't have a calculator on me, or do I somewhere? Not seeing a calculator, but it's not going to be a problem for us, guys. Here's what's going to happen. This is the sigma squared. This is a sigma squared here. It's a bigger capacitance because of this. The bigger capacitance on the bottom gives you a smaller answer. This value right here um, 1/2 Q squared D over, that is that right there, the bottom thing is a smaller number than what happens here. So this is 1/2 just some commentary on this at the end of the day on this. We'll see. Maybe just leave it like this for now, and we can kind of talk. Well, I'll make a long story short. Epsilon naught sigma times sigma is epsilon naught sigma squared. That's good. Then you got all this too that comes around with it. So it's going to be a bigger answer on the bottom. So this is bigger. The initial situation before you inserted the dielectric, there was more energy stored than the U final. You know, and that was, you can call like the U, you can call this U right here the U final. So there's some commentary we can make regarding this. What's going on here? This thing basically lost, with the insertion of this thing lost potential energy. So lost potential energy. So let's see exactly how the commentary works on that. You can look at this and see where it's going to go and actually work it out and see what kind of force we're talking about. This is, it wants to go to a lower potential energy. It's going to draw this thing inward by the looks of the whole thing, the way they got it set up. What happens is, so this is the general formula. Now look, when kappa is equal to 1, guys, when kappa is equal to 1, it means no dielectric. When kappa equals 1, it's no dielectric. 1 minus 1 is 0. 0 times y is out of there, and you just got this. Epsilon naught sigma times sigma over d. That was this. And that was a higher potential energy when it had that. When that got put in there, the potential energy fell. So it wasn't really fighting the introduction of the dielectric. It was accepting it and going to a lower potential energy. So you look at this situation, you say, well, what is it? What's y? And the y is the bigger as y changes, is y gets bigger. What's going on here? What's happening? So, okay, we did this. We got the answer here. Let me kind of... All right, so we can write this as a general formula. Can write this as a general formula, guys. And why can we do that? Because everything's okay if you're going to talk about the kappa being equal to 1. We're talking about 1 minus 1 is 0, and that's it. That's the end of the day on that. The force vector what's going on in relation to this? It's negative du dy. So as y increases, delta u gets smaller. We already kind of mentioned that here. As y was increasing, delta u was negative. So negative divided by a positive is negative, and the opposite of that is negative of a negative. So du dy is going to be a negative answer. Negative of a negative is positive. So You do this, do the derivative. It's a bit of a complicated looking scenario. It's not really difficult, but it's a little on the tedious side. When we actually do it, we've got let's make sure I'm not entirely thrilled with my notes. No, they're believable. Yeah, everything is believable, guys. F over G is G F prime minus F G prime, right? And the whole thing over here. Yeah, it looks good, guys. All you got to do is put the square here. Yeah, negative of a negative is positive. These are all positive numbers. Yeah, they're all positive numbers here. And like I said, this changes. As y is small, the bottom is small, which makes the answer big. If y gets bigger, the bottom is bigger, and it makes the answer small. So the u is decreasing. For there to be a change in potential such that you're losing potential, there's an attractive force drawing this in. And that's, you know, so it's coming to here, and then you grind out the answers. I'm not, I don't know that it's here, guys. So we got this. There we go again. So it's easier than it's written. I guess we could say that. And it's this guy squared. You know, pick and choose how you want to write these guys, but for it to, it'll go, the force will draw it to a place where it's going to lose potential. So it's going to be drawn inward. There's an attractive force inward, and the internal energy decreases by virtue of the fact that there's work done to bring this thing in. Pretty fascinating stuff that way. It's just like something that falls from a height. It has less, it's going to where there's less potential energy. That means the force is drawing it to where it's less potential energy. This is being drawn to where there's less potential energy, and so it's being drawn into it. Yeah, and and they actually just gave an answer here as well. So drawn inward. From here and from our talk, okay, drawn inward, drawn into the situation where there's a tendency a force to draw it inward. Toward the dielectric being there. It's less potential. It's a circumstance of less potential energy, and it's being drawn into that. What are the magnitude and direction of the force exerted on the dielectric by the plates of the capacitor? As we just said. All right, guys. Thank you very much for your time. Take care. We'll talk soon.